I will show you how to calculate potential for a conservative vector field, and it can be done in any dimensions. I will start with two variables. Vector field is conservative if the line integral depends only on the starting and terminal points on the curve gamma. And it can be written as value of the potential at the end minus value of the potential at the start. The shape of the curve is not important. We have only start point and end point. If you take any curve that connects start with end, you will get the same integral here on the left, the same value. And it's always f at the end minus f at the start. The question is how to calculate formula for potential. And I'll show you a very efficient way to do that. First, I look at what I have now at the definition of conservative vector field, and I will move this f at the start to the left of equal sign, and I have already formula for the potential. F at the end is equal to this integral plus some constant, which is the value of your f at the start. Now let's calculate this integral, and this integral can be calculated along any curve you like. The only condition on this curve, the only requirement is that the curve starts at the start point and goes to the end. It connects those 2 points. Otherwise, it is completely arbitrary curve. Now, let's start with frame of coordinates. I'll take standard frame of coordinates, orthonormal frame of coordinates in x1, x2 on the plane. And my start point, I will put at the origin. This is my start point. And my end point is arbitrary. It could be anywhere on this plane. Let's put it at the point with coordinates alpha and beta. This is my end point. I can take any curve connecting start with the end, and the integral will stay the same. Since it is the same, I'll choose the curve that I like. First, I will go along x1 axis. I will go along x1 axis until I reach point alpha. I do alpha steps along x1 axis. At this point alpha, I will make 90-degree turn, and I go vertically up until I get to end point. And that's my curve. It starts at the origin, it goes till the end point. Now let's calculate this integral. My red part of the curve can be parameterized by x1. All points look the same. It's x1, 0, and I take x1 between alpha and 0, and I can label all points with x1. And blue part can be parameterized with x2. x2 is taken from beta, from 0 to beta. That's my parameterization. And now I can write formula for the potential. Integral along red part, it's integral from 0 to alpha, f1. You see, x2 doesn't change. It means change in x2 is 0. I have only f1 part left. And now the second part. I am done with the red part, with this red line. Now I go along vertical blue line. The curve is parameterized by 0x2. Alpha x2. x1 equal to alpha, and x1 doesn't change. It's always alpha here. That means change in x1 is 0, only f2 left. And I have integral from 0 to beta f2. Now x1 is alpha and x2 is summation variable. And f at the start, my f is it's the value at 0, and it could be any constant here. And now I have nice formula for the potential. Since it's correct, it's true for any alpha and beta, it works for any alpha and beta, I can replace alpha and beta with x1, x2, and I have nice formula for the potential. So first you calculate integral of f1, x1, 0. Then you freeze x1 in f2. So you have already calculated integral with respect to x1. Now in the second integral, you freeze this variable. You freeze x1. x1 already used before. You calculate with respect to x2. And plus constant. This is the formula for the potential. Of course, there is no specific preference for x1, x2. x1, instead of x1 going first, actually you can use x2. Instead of going horizontally, I mean along x1 axis, you can go vertically at the beginning until you reach beta, and then you make 90-degree turn and you go parallel to x1 axis. You can flip x1 and x2 and you still get the potential. So it's still the potential. So if you flip variables, first you go vertically along x2 axis, and then you go horizontally parallel to x1 axis. And now in the second integral, x2 is frozen because you used this before, and x1 is summation variable plus constant. And that's how you can calculate the potential for two variables. You can do the same steps for three variables as well. Let me do it for three variables. Again, vector field is conservative for three variables if this integral doesn't depend on the curve. It depends only on starting point of this curve and terminal point of this curve. Otherwise, you can take any curve that connects the same points and the integral stays the same. And if it is the case, then you can find the potential. The integral will be equal to value of the potential at the end minus the value of the potential at the start. And again, it depends only on start and end. Start, end, and any curve in between will do. It will create the same integral here. Again, I will write f at the end, just move this f at the start to the left of equal sign, and basically you have already the formula for the potential. You just need to calculate it. Plus f at the start. Again, I do it in three variables, exactly in the same manner as I did it for two variables. I take orthonormal frame, I take this orthonormal frame, and I put my starting point at the origin. The origin will be at the start. Then, and I take any arbitrary point. It could be any point in three-dimensional universe. Let's call it alpha, beta, mu. And now I can choose any curve that connects start with the end. And I choose very specific curve. It goes along coordinate lines. First, red part goes along x1 axis until I get to value alpha. Then at this point alpha I will make 90-degree turn, and I will go parallel to x2 axis. Then at the point, when I get this point alpha, beta, 0, at this point I will go make 90-degree turn, and I go vertically up. I go vertically up. Yeah, something like this. And I reach the end point here. Now I calculate my integral for this specific curve gamma that connects start with the end. I can parameterize each line here, each segment here. The red line I parameterize with x1. This is my parameterization for the red line. x1 is label, and x2, x3 are both equal to 0. I need to take x1 from 0 to alpha. Now blue line I can parameterize, I can label with x2. x1 is equal to alpha, it is frozen. x2 is my label, and I need to take x2 from 0 to beta. And the green line I will parameterize with x3. I keep x1 and x2 frozen, and x3 is my label. x3 goes from 0 to mu. And now I parameterize my curve, and I can calculate the integral, and it will give me a nice formula for the potential. So f at the end, my end is alpha, beta, mu. It is equal to first integral with along the red line. x2, x3 always zeros. That means change in x2, change in x3 is equal to 0. I have only integral of f1 here. And x1 goes from 0 to alpha. So I am done with the red line. Now I go along the green line. x1 is alpha, x3 is 0. They do not change. That means change in x1 is 0, change in x3 is 0. I have only integral with respect to x2 of f2. In this integral, x1 is frozen. It is equal to alpha. x2 is changing, and x3 is 0. And finally, the last integral along green line. It goes from 0 to mu. Now x1 and x2 are both frozen. x1 is alpha, x2 is beta, and x3 is alive. It's summation variable, and it goes from 0 to mu, plus the value of f at 0 at the start. And I have nice formula for the potential. Since I can do it for any alpha, beta, mu, for any end point, I can replace alpha, beta, mu with x1, x2, x3, and I have formula for the potential. That's the formula. It's a very nice formula. It's easy to use. Integral from 0 to x1, f1, x1, the rest is 0. Integral with respect to x2. Now in f2, x1 you already used in the previous integral. You keep it fixed. Whatever you used before, you keep frozen. x2 is alive, the rest is equal to 0. And finally, integral with respect to x3. Now you have already used x1 and x2. That is why you keep them frozen here. You treat them as constants when you integrate with respect to x3. And plus f at 0, it could be any constant here. And now you have nice formula for the potential. Of course, you can shuffle those variables as you wish, because instead of going along x1 axis, you can go first along x2, then x1, x3, or first x3, then x2, x1. There are many choices. You can shuffle them and still get the formula for the potential. And you can do the same for n variables. So let me do it for n variables. Again, vector field is conservative if this integral depends only on start and end points of the curve. And it doesn't depend on the shape of the curve, as long as this curve connects the same points, start and end. And it's equal to f at the end, that's potential, minus f at the start. And regardless of curve gamma that connects start with the end, this integral stays the same. You see, it doesn't depend on curve gamma. Only it depends on start and end points. So I will use this definition, and based on this formula, I can write formula for the potential. It's right here. F at the end is equal to this integral and I will move f at the start to the left of this equal sign on top, plus f at the start. Now I choose my start at the origin, and I do exactly the same steps, and I can write final formula for the potential. Exactly the same steps. I will take gamma that moves along coordinate lines like that, and I calculate the formula for the potential. It's easy to see that it is equal to that. First integral from 0 to x1. You take f1 here, x1 is alive, the rest is equal to 0. Then the second integral with respect to x2, now you take f2, you used already x1 before, you keep it fixed, treat it as a constant, you integrate with respect to x2, the rest equal to 0. Then you do the same for x3, integral from 0 to x3, integrate f3, now x1, x2, you have already used x1, x2, you keep them fixed or frozen, you treat them as constants, x3 is alive, the rest is 0, and you keep doing that. In the next integral, you integrate f4, x1, x2, x3 will be fixed, x4 is alive, the rest variables are zeros, and so on and so forth. And finally, it's the very last step. You take integral with respect to xn, fn. Everything is frozen. You treat all variables as constants, but the last one is summation variable, it's alive. All the variables I used before are frozen. You treat them as constants, and you calculate this integral plus the value at 0, which could be any number. And you have nice formula for the potential. Of course, you can shuffle variables. Instead of x1 could be x2 first, or xn, whatever, and you still get the potential. Just one remark. This procedure works even in those situations where vector field f is not conservative. When you calculate small f, when you calculate prospective potential, you still need to check that gradient of small f matches your vector field. Gradient is the list of derivatives written in the same order as you have variables. So you need to take gradient and make sure it matches capital F. If it is the case, small f is the potential for capital F, this potential function for capital F, if it is the case. That's the only thing you need to check. It has numerous advantages in comparison with what you can find in common textbooks. First, capital F it can be as ugly as you wish. The only thing which is required is to be able to take those integrals. Otherwise, it can be anything. You don't need to differentiate it, nothing. And it's much more natural and easy way to calculate the potential than you can find in most textbooks. Thank you.